We are now switching over to lightning talks. So Arnaud Spivak is going to give our first lightning talk. If you are also doing lightning talks next, come on up. I believe we have five. So I'm going to try keeping us pretty closely to 5 minutes when we're doing that. But and you feel free to go ahead and set up. And if you're coming next, let me know.
Who's next?
Who is next? Nikki, who's next?
May need to do. I'm already there. I seem to. Okay. I need to mirror displays, I think. Absolutely. What? Or I'll have to do it blind, which is going to be very interesting if I have to do that. Okay, it's not opening. So where am I? Here. This is going to be hilarious. It needs to be. It's about the right size. Okay. Come again? I still haven't heard you. I don't hear. I can't hear the question.
Is it night mode? Is that what you're talking
Oh,
about?
it is night mode. I can remove it. Yeah. Yeah, because it's I didn't change the time zone, so here we go. Is that better? Oh, that's much better. Yay. I'll be happy, but I don't see my screen, so it's going to be interesting because I'm presenting off a. I don't have slides. I'm just presenting off an Emacs buffer, which is very talkative today. Okay, hello. We get started, I guess. Yes. Okay. So this is a lightning talk that had the fortunate happenstance of having just gotten a 1 hour introduction. So I want to think back about the two talks we just had. And they were about property-based testing, but they didn't really talk about properties all that much. They talked about generators and shrinkers, right? Because properties are pretty much always the same all the time. They're not very different. And you have like a gazillion libraries, and they differ by generators and shrinkers. I'm going mostly to speak about random generators in this talk and shrinking, because that's the bit I know best. But I don't think what I'm going to talk about is particular to randomness, and enumerative testing probably works there too. Though I haven't thought about it, so I may be wrong. The problem I have with all that is that these probably like about 15 testing libraries that we have in Haskell all define a property type. Despite the fact that it's always the same thing, ish. And the thing it is IO unit most of the time. Plus some stuff. The fluff around the IU unit is important, but the main technical content is IU unit, and you interpret return as success and exceptions as failures. And that's what a property is, and then there's a good number of ways to build properties. If you think about it, it's not really like super surprising. IO unit is the type of Haskell program, so IO unit is like the maximally powerful type. You can do everything you want with it, and the minimally observable type. You don't know anything about it. That's why you need some stuff on the side very often. And then you have some kind of monad to generate choices, and then you have a for constructor that says, well, if I have a property that depends on a particular value, then I can generate values for that property and test it. And then your test thing will maybe run the properties 100 times or something like that if it's to test them on various values. Yeah, so the monad probably needs to be an IO monad and stuff like that. It doesn't matter for today. And maybe it's not really IO of unit. Maybe you need more context. But that's the base of the story. By the way, this I can compile this buffer. It's a real Haskell buffer, but it doesn't run anything. And don't obviously. So my point is, I can make a type of generator. I'll put that well in the middle. I typed a V. Fantastic. Okay. So I can make a type of generator that contains all the generators for all the libraries. So these libraries exist, they have different kinds of generators for a good reason. They're constrained in certain ways so that they can combine nicely. That was the whole point of Haskell's talk earlier. So when you inject in this type, you will not have very good combination properties. So you don't really want to use this type all that much. But you can use this type to define the for all combinator that we just saw earlier. And so what we're saying here is there's an existentially quantified x here. So there's some internal state. We can generate stuff of this internal state, and we can show it as an A because we want to generate A, or we can shrink it to smaller x's. And that's all. Plus everything you need for display, printing, because you want to show your counterexample, so of course you need a way to print the A's and stuff like that, of course. And these are, the niceties are the important bit, and I'm just focusing on the technical part there. So just as a demonstration, I'm going to take three favorite libraries of random testing and show how they can inject. So in type check, you have a type class. It's completely, it's not important, but I decided to use the type class nonetheless. You have some monad. Here I just fixed a random monad that I call genm that generates to an A, and then when you have an A, like we have a list, you can make a smaller list by removing the first element, for instance. That's kind of how it works. Or you can remove any element and make a smaller list. That's the general idea. Well, generators generate directly A, so displaying or passing an A is just the identity, it's already there, and the shrinker, well, the shrinker is just given above, so it works. I should say something about gen. So if you are familiar with imperative encodings, or, well, it's just the type of an unfold, basically, right? It will differ because of the nicety. So you could come up with a data structure. It's a nice exercise a co-inductive data structure that would avoid the existential quantification. But I think it's just easier to use it that way. Anyway, hedgehog is completely misaligned. Ooh, yeah, thanks delay. Okay, we can almost see something here. Here we go. I hope you can all see. Maybe I centered a bit low. Isn't this better? Yeah, maybe. Hedgehog, we saw the type of hedgehog. It's over there too. I have 1 minute. Okay, well, it's good. So these are trees. In that case, the internal state is tree. So you generate trees, and the shrinkers is just passing the tree, and then we have Gumgan, falsify here, sorry, that just, you generate a sample tree, the internal state, the X is the sample tree, and you iterate on it. And then you can implement for all. And so you could implement for all of these libraries directly as well, because it's covariant. So I have, I'm done with my slides-ish. So I'm going to conclude by saying that this talk is less a talk than a call for action. I will not be implementing this. I think Haskell needs a library of property that is generic and can use the properties for every other libraries. There's a lot of thoughts to be put into it to have good UX, have good error reporting in case of failures, and to actually support all libraries. For example, Hedgehog over there was a simplified model of Hedgehog. Hedgehog does mutations, or, well, not mutations, effects in many, many places, and you'll have to be able to take care of that. This is not an obstacle, it just makes the model less simple, and you have to care about that. I am happy to advise or to help out anyone who would take this particular task up. So you can come and see me, I'm here until lunch-ish, otherwise you can find me online, and
thank you.
Yeah.
We can take one question as we're changing over the setups, but no more than that. Harry.
I'm curious if you've seen the infrastructure that we built into Etna, the PBT evaluation framework that was presented earlier this week?
No,
Okay, we should chat offline.
thanks.
All right. Thank you very much. Our next speaker will be Armando Ramirez from Mercury. And just a reminder for everybody, I'm going to be flashing like time signals at you. So we're going to try to keep it to 5 minutes because we have 5 people who want to give talks and about exactly enough time to do that. So please try to keep to your 5-minute slots. Once this goes up. Yes, sorry, and Joachim is next. Then you.
Is it not working? Oh wait, let's mirror. There we go. Let's see, can you hear me? Can you hear me? Okay. Okay, so I'm Armando Ramirez. I'm a Haskell engineer at Mercury. I also do some Haskell game dev on the side. I'm going to go over just 2 fun tricks to help you guide inference when you're doing some kind of weird, advanced typey stuff. So, what's one situation where type inference fails? And the classic example is when you have some sort of multi-param type class, you have some sort of polymorphic usage of it, and then you get poor inference. So what does that look like? Basically, GHC can't figure out what that R parameter to monad reader is, because length is polymorphic in the foldable, polymorphic in the A. So this happens in a lot of situations. Function composition, overload, records labels. Now, for this specific example, I'm aware you could just slap a fund up on it, call it a day. But you can't actually always do that. For instance, if you're using extensible effects, and you have a reader in your effects stack, maybe you have 2, maybe you have 1. If you build this, you also get an issue due to ambiguity, whether you have 1 in there, or you write polymorphically over the list. You also get it. Now, when you're polymorphic over the list, it's fair for there not to be, for inference to fail, because there could be 2 in the list. But in this case of no inference, when the concrete list, like I'm staring at the 1 reader, why can't GHC find it? So let's give it some help. And let's prove to GHC that there is 1 in the list. So in this case, this is kind of the API. We say that there is the effect in the list. So you have this is the higher kind of effect, like reader. This A is the parameter, like R. And this is the list of effects that we're searching. And then all you do is you just, instead of having a member constraint, you have a the constraint. So you say in this list, there is 1 reader, and the reader has a type of R. And then you just have as the, and then it just works. And then down here is just all the guts, the type level guts of just traversing the list, making sure there's not duplicates, making sure there's not duplicates, both literal duplicates and 2 readers of different types. And you get nice type errors for that. So let's see this work. So here's basically the same program as before. I just replaced asks with asks the. And it builds. And it also works when you just bring the constraint in yourself. And just to show off the fancy type errors, you do get yelled at if you have a duplicate, and you actually don't have like a canonical thing in there. So this is kind of a way to decouple that fundep from the type class, and you can kind of bring it on a la carte as you need it. And that's pretty useful. It's useful. I find it useful in effects. I'm using clef here, but sometimes you do want 2 readers, and depending on your scope, you want one to be the one that we want one to be the one that inference is focused on. So I have a way to do that too, and this is a little weirder technique. You basically you can use an implicit param that's a proxy, and it's parametric in R. Now, implicit params are always concrete. So basically what happens is you just slap that constraint on there, and then when you call this, that R is fixed, and then that helps guide GHC to find the reader that you're looking for. And I have this with imp reader, just so you don't have to use, it's not nice to use implicit params directly, but it's not bad this way. So here's a simple way to use it. Here we have 2 readers. We do with imp reader, then in this block, everything will be guided towards the reader list of ints. In here, it's guided towards strings. This program works. I think it's not as useful for this, but say you had you could put a do block in there with state. You have multiple states focusing on them. I can imagine this being useful for just if you have something very type level-y, type directed, and you need like some UX stuff so your users can not put 10 type applications at every use site, but just like one type application that goes to the block. So that's it. Those are the 2 tricks. They were meant to be fun, but also useful. And if you want to look at the code, it's on my GitHub, Ramirez7. Thank you.
Thank you very much. Once again, we've got time for a question as things change over. And if not,
No, it's just Simon. It's just. But I could. It's just like, yeah, I could release the bug. Oh, and the why I guess I said out of time. The reason I did this to begin with, there is a GHC plugin for the extensible effects that does this for you. But I was cross-compiling, and it yelled at me for using plugins, so I just had to do it in typespace land.
alas. All right. Our next speaker is Joachim Breitner.
Okay, who saw my talk on Tuesday? I made a mistake there. I made a claim without testing it. I said I can, this idea can allow you to write a parser combinator library where left recursion works if you have sharing. And I didn't actually try it because it was obvious it would work, but people didn't like that, so more progress. So here's a conventional parser combinator library. I took this code from the Arcta code base. And with these parser combinators, if I write a parser, this is a parser that detects sequences of A's with left recursion. Oh, is this big enough? Probably not. Then if I use this parser, it will just hang. So this is the problem with left recursion in parser combinators. Now this particular library has a memoize operator where I can make the recursion explicit by giving a unique key for this, this rule, and then it works. Now my claim is I can take these kind of slightly imperative ways where you have to be explicit about recursion, and if you use sharing, it works. So let's read another file, has this, loaded, and then try this again. So here's the recursive definition with no explicit annotation for the recursive thing, and it works. So how does this work? We can look at the code briefly. This is the module. It is a new type wrapper around the. Is this bigger? It's a new type wrapper around the library, and then of course non-recursive combinators I can just wrap normally. And this is all the magic. This is this combinator called propriocept, which tells a thunk about its own identity. So you can use it to create a thunk that has a unique. And different thunks will have different uniques. And with this, the name basically, of course, is Richard Eisenberg's input. I didn't know about this word before. And I can use this to create a combinator called withmemo, which takes one of these underlying combinators and turns in a new combinator with my abstraction that uses the memoize function. And now all the combinators that may possibly be recursive, which in this case are functor, applicative, monad, alternative, I just use withmemo. So they know about their uniqueness, and now I can do this thing. And here's a larger example. Okay, I'll also make the font larger, so that the example is even larger. A simple data type for grammars, and now a grammar to parse BNF syntax. And there's some left recursion here. I mean, I don't look at the details, but here BNF is left recursive in BNF. And let's try to use this. So I can now try to parse this. Okay, I'm now using this BNF parser that I defined. Sorry, wrong window. On this BNF syntax here. So a BNF for numerical expressions, and it doesn't work. This is the not tying trickiness. This is a left recursive definition that doesn't do sharing. It's like a lexeme combinator. You see it calls LP itself, but it's not sharing. But I can make this. I can use the usual, like just when you do not tying in Haskell normally, you make sure that the recursion goes through a local let definition. And if I now reload, this works, and I can parse this thing using left recursion grammar. And of course, the benefit of having a parser combinator is I can now use it dynamically. So I can, for some reason, I just parsed a BNF grammar. So I can interpret that data structure now into a grammar. And again, the grammar that I just defined is left recursive all over the place. But because my interpretation is careful to be cyclic, it's using this map of parsers and it's using them below, I can now take this BNF description, interpret it, and then parse expressions with it, even though it's left recursive. Oh, I have 30 more seconds, but I'm done. So you can go over. Take 2 questions.
Yes, as is a tradition.
So there's a reason why unsafe before my O is called unsafe before my O.
Thank you,
And
yes.
yet using it in some kind of safe way. Can you think of some kind of primitive operation you could end up making a respectable, reasonable about thing?
Well, I think there's always going to be some layer where you have to. So in this case, I think the code here is using unsafeness, but then the API I provide will be safe again. The argument here is, which I haven't verified because I haven't written the library below, that it doesn't matter to the memorize function, to the underlying parser, if you, like what the precise key is, you pass there and you can't observe that, and then it becomes safe again.
Let's talk about the laptops.
Yeah, so go ahead.
And also, the next person I have, I can't read my own handwriting, but your name begins with an L. Okay, so only one other person who I think has to do this, so please come up. Okay, any? No. You're good. Yeah, okay.
No more questions? Good.
Richard does need the mic.
I can try to do forward.
He is pretty loud, but for the general benefit. So yes, our next speaker will be Richard Eisenberg.
Okay, is the mic picking me up?
Sure is.
Yes, and the video is picking me up too. Good, okay. So I just wanted to share a little bit of work I'm doing because it might be of interest in the Lightning Talk, so why not? This is ticket 23162, which is a small improvement to the inference around closed type families. I don't have a full motivation here up on the screen, but the actual motivation is there was some proposal that introduced names for all of the tuples, and there was some grand type family that counted up to 64 and figured out exactly what tuple you mean given a number, but it turned out that the inference around that was bad. So I thought, let's just improve inference. So let's say we have a type family like this, TF, and note that TF is not injective. There are 2 different arguments, int and double, which both map to car. But actually, if we know that the result is this one here, then we can actually infer, we know that the argument has to be bool. And I have some function f. Obviously, we can't define f, but maybe there's a class constraint or something that would allow us to define it. In general, you can. But then I want to look down at here. If we have g, bigger. Okay, is that better? Yes, good. Okay. So G is just a call of F, and but it doesn't do it. What it does is it constrains that the result of F is a maybe of something. It doesn't even. It's not even necessarily maybe integer, but we know that the result has to be a maybe something. So right now, if I try to infer the type here, I can say GHCI of this thing, and ask what is the type of G, and we get this. It works. GHC can infer this, but it gives me this big type and says, okay, the result of TF has to be a maybe, and the original thing has to be showable, and that's kind of a pain. In the actual motivating example, it doesn't even compile because things are just much more complicated, and there's like a class constraint that can't get solved. If I use my development branch here, build, what do I have to say, stage 1, bin GHC interactive of lightning, blah. Okay, so now it loads, and now the type of G is this nice bool arrow string, right? Because it uses the fact that TF is closed to say, well, if the result is maybe, then there's just only one way to have done that, and it has to be bool, and why are we messing around with anything else? Unfortunately, not all is well. And this means I have to redesign how functional dependencies work in general. You pull on one little piece of string and then the whole thing unravels. So here, I took that type signature that GHCI reported back to me, and I put it here. It's the same type signature. The only thing I've done is I've had to add this call to this silly type function id, and that's just to confound the type checker. The type checker is clever enough, if I don't put the id in here, then the effect that I'm looking for won't happen. But now, if I try to reload, it fails, saying that the type of H is ambiguous because it can't, let's see, I probably don't have quite enough time to explain exactly why. There's a lot going on here. The problem is that this constraint here doesn't, in GHC's telling, does not tell me that A1 has to be bool. I don't get a given from this constraint that I can then use to prove that A1 equals bool. I can only sort of infer it. And the solution is going to be wait to do functional dependencies later. I can say more in the break. But in any case, I thought this was kind of fun and wanted to share. That's it.
All right, once again, while we're switching up, you feel free to ask questions. What happens if there are two cases matching, but not all of them? Do you get a disjunction of things?
No.
Can you have
It's just you don't make any progress. I mean, although if you had maybe bool and maybe integer as two different possible results, and there was something similar about the arguments, it would be able to infer that.
Oh, nice. Thanks.
I think. Sounds plausible.
And our final speaker for the lightning talk session is Laute Stegeman, who will be talking to us about this.
Okay, thank you. And thank you for pronouncing my name pretty close to the correct pronunciation. Okay, so this ICFP, I've been getting a few questions about GHCDS, whether it's dead or not, and some people don't know about the GHC JavaScript backend, so I'm going to give a brief introduction, say what the status is. Briefly, it's the GHC backend for JavaScript. Everything has been integrated into GHC. It uses the Haskell to core to STG to JavaScript pipeline. There's no CMM involved. We depend on Mscripton and Node.js, but Mscripton is mostly used for basic toolchain things. We don't really support compiling C sources directly to JavaScript. A bit of glue is needed if you actually want to use Mscripton compiled sources. It's based on GHCDS. We fixed a lot of things. Everything is built with or tested with the GHC test suite now. We found a lot of things and it's improved, but also a lot faster. But some things are still missing. If you're used to GHCDS, then optimizer is missing. You still get bigger executables. We're working on that. Incremental linking is missing, splitting your executable into multiple things, and the convenient JavaScript or the convenient foreign import syntax with the $1, $2 placeholders is still missing, but basic syntax works, so it's very easy to convert things over. So why are we doing this? Well, the original motivation was to build, to make Haskell accessible in browsers, and also scripting on Node.js compile something that you can just deploy everywhere else. Everything is bundled, and you can use it instead of shell scripting with nicer type safety and stuff. I'm interested in finding out what the kind of things we need from Haskell in a managed runtime. If we don't do bit manipulation and are a bit higher level, what features do we need? For example, we have special weak references, ephemerons, and we can often get away with simpler things. And for example, from the WASM people, we had the questions a couple of times, like what kind of features do we need from a garbage collector or for fast pattern matching? So really the JavaScript pipeline is a pipeline for a managed runtime, where maybe we can use these kind of things in the future to answer these questions and experiment with it. Another thing that I really like for being a sort of higher level output for GHC is that we can often use the JavaScript or V8 tools to inspect the heap and to get more information about our Haskell programs. It's much more, I get less headaches using V8 and the graphical tools to inspect what my Haskell program is doing than using GDB or LLDB. So I hope we can at least keep it alive for that kind of things. So where are we? In 9.6, everything was integrated, was merged. We could do Cabal simple install, but not the custom scripts. and we didn't have template Haskell. Those were fixed in GHC 9.8, so most things you could install with GHCDS, you could now install with the backend. Later we'll get the optimizer and profiling and better FFI, but let me get a quick introduction of some things where you might be able to help. If you have packages that work with Haskell and you have some C sources, some things that are not Haskell, then you might, to get them supported with this backend, write a bit of JavaScript. You can use the cabal flags that test for the JavaScript architecture and add your JavaScript files to your package and write a bit of JavaScript glue code that just does the work of the non-Haskell code in the existing packages. So for simple examples, if we have, say, a function, a memcomp function, which takes 2 pointers and a number, and we check whether the one of the memory regions is bigger or smaller than the other. Pointers are represented as pairs. AV and AO are A value, A offset, BV, B offset. There's a bit of data structures involved that are not very complicated, and usually it's there's a bit of manual work involved in converting it, but it's fairly straightforward to convert existing C code to JavaScript code that works with a different memory representation. Sometimes there might be more specific things like Node.js. You can do scripting, do processes that aren't available everywhere. We have some utilities to help with decoding, convert from Haskell C strings that are pointers to JavaScript strings, and platform detection for features that might not be available on all platforms. So if you want to help, then it's nowadays very easy to install. This was a hard question or uncomfortable question, but you can. These 3 lines are enough. You need Emscripten. After you configure your GHC, you can build it with Hadrian, and then you can use Node.js just to test the generated JavaScript. You can also use GHC up and Haskell.nix. Haskell.nix is useful for CI. There are some things involved, a few more steps to activate the right testing repositories, but it's really quite easy to install. And if you have something that, oops, that's the last thing of my slide and also the last second. If there's something broken, then please tell us. It's easy to test now. So thanks.
Thank you. There's one quick question we have time for, exactly one quick question.
So is there any plan to have some sort of FFI for C, like C to JavaScript or Emscripten? There's certain libraries do, like SDO2, how to JavaScript, and it'd be nice to be able to just have a bot kind of understand how it is.
The question is there a way to do FFI to C from JavaScript? Just to, yes?
C compiled to JavaScript.
C compiled
Yes.
to JavaScript.
It's already possible, but since we have a different representation of our memory, all the C is compiled to something where pointers are all pointing to the same buffer. And with our managed memory, where all the Haskell heap objects are separate objects and stuff, we support multiple buffers. So there's a slight impedance mismatch, but usually it's very easy to write a few lines of glue code between the Haskell code and the C code. And we've done that for IOG with crypto libraries. So, yeah.
Thank you. Let's thank all our speakers one more time.